Welcome to lecture 15 on measure and integration. In the previous lecture, we had defined what is called a measurable function on a measurable space x s, and then we had looked at some equivalent ways of looking at measurable functions. We looked at examples of what are called simple measurable functions. They are nothing but finite linear combinations of indicator functions of subsets of the set x. The simple measurable functions are sort of the core of the class of all measurable functions. We showed that sum of simple measurable functions, product of simple measurable functions, and maximum and minimum of simple measurable functions are all simple measurable functions. And today we will start looking at some general properties of measurable functions f, and then we will characterize measurable functions in terms of simple measurable functions. So, today's talk is going to be mainly on properties of measurable functions. So, let us recall, for simple function we defined what is called the positive part and the negative part of a function. So, this can be defined for any function. Let f be a function defined on x taking extended real valued functions, extended real values r star. Then we define what is called the positive part of the function. So, that is denoted by f plus of x. This is again a function on the space x, and it is defined as f plus of x is equal to f of x if f of x is bigger than or equal to 0, and it is defined as 0 if f of x is less than 0. Essentially, what we are saying is, look at the graph of the function f of x. As long as the graph remains above the x axis, keep the function as it is. So, f of x is kept as it is if f of x is bigger than or equal to 0, and as soon as the graph goes below the x axis, we define its value to be equal to 0. So, this is called the positive part of the function. So, note that for any function f, the positive part of the function is again a function on the space x, but it takes only non-negative values. And similarly, we can define the negative part of the function to be a function on x again, such that, and it is denoted by f minus of x. So, f minus of x is equal to minus of f of x. Keep in mind, we are putting a negative sign here if f of x is less than or equal to 0. So, that means, as soon as the function is on x axis or below the x axis, we reflect it against x axis and put its value as minus of f of x. So, f of x with a negative sign. So, if f of x is negative, so this will always be a non-negative quantity, and it is, the function is defined as 0 if f of x is bigger than 0. Essentially, once again it is looking at the graph of the function. As long as the graph of the function is above the x axis, we put it value equal to 0, and it is minus of f of x if f of x is less than or equal to 0. So, these are called the positive part and the negative parts of the function, and it is quite obvious from the definition that f can be written as f plus minus of f minus. So, and we want to prove that if f extended real valued is a measurable function, we want to show that in that case the positive part and negative part are both measurable functions, and conversely, if positive part and negative part are measurable, then the function f is measurable. So, namely saying a function f on x taking extended real valued is measurable if and only if both f plus and f minus are measurable functions. And the proof is rather simple. So, let us assume first f is measurable, then for any point c in R, look at the inverse image of the closed interval c to plus infinity. So, f plus inverse image closed interval c to infinity. So, that we know is because f of x, f plus of x is equal to f of x if x is f of x is bigger than 0. So, if this value c is bigger than 0, then f plus of x will be equal to f of x. So, this inverse image of the closed interval c to infinity under f plus is nothing but the inverse image of f of the interval c to infinity if c is bigger than or equal to 0, because in that case f of x is always going to be positive, and it is equal to the inverse image of the interval 0 to infinity if c is negative, because then we do not want to look at the remaining part. So, in either case, because f is measurable, both these sets are in the sigma algebra. So, f plus inverse of c to infinity belongs to the sigma algebra if f is measurable. So, that proves that f plus is measurable. A similar argument will prove that f minus is also measurable. So, essentially what we are saying is the f plus inverse, that is the inverse image of the interval c to infinity under f plus, can be represented as inverse image of interval of f under f of some interval, and both are f measurable implies that both whenever that f inverse of an interval is a set in the sigma algebra. So, we have shown that if f is measurable, then f plus and f inverse are f minus are both measurable. Let us prove the converse part. Suppose both f plus and f minus are measurable, and let us take a point c belonging to R, then we should show that the inverse image f inverse of c to infinity belongs to the sigma algebra S for every c in R. So, let us fix a c and look at this, and we have to interpret this in terms of inverse images of some intervals in terms of f plus and f minus. So, now let us observe that the inverse image of the interval c to infinity can be decomposed into two parts, let me f inverse of c infinity intersection 0 to infinity. So, look at the intersection of c to infinity with 0 to infinity, and the intersection of this interval c to infinity with minus infinity to 0. So, this interval c to infinity is decomposed into two parts, its intersection with minus infinity to open interval 0 and its intersection with closed interval from 0 to infinity. So, f inverse of c infinity c to infinity is nothing but f inverse of the inverse image of the interval c infinity intersection with 0 to the part of the interval which lies in the positive part, and inverse image of the part of the interval which lies in the negative part. But that means, in the first part we are looking at whenever the function is in 0 to infinity, that means the function is non-negative. So, the first inverse image is nothing but the inverse image of this same interval under f plus, and similarly the second one is the inverse image of the interval c infinity into intersection with minus infinity to 0 with respect to f inverse. So, the part of the function which lies in 0 to infinity is written as inverse image under f plus of an interval, and the other part is written as inverse image under f minus. Since both f and f minus, f plus and f minus are measurable functions, so these two sets f plus inverse of that interval and f minus inverse image under that interval, these both are sets in the sigma algebra S. So, their union is also in the sigma algebra S. So, that means f inverse of c to infinity is in the sigma algebra for every c belonging to R, and that proves that this is f is a measurable function. So, we have shown that a function f is measurable if and only if its positive part and negative part both are measurable functions. Next, let us look at some more properties of measurable functions. We want to give a characterization of measurable functions in terms of simple functions. So, we start with a non-negative function. Let f be a non-negative function defined on x. So, taking values in 0 to infinity, we want to show that this function f is measurable if and only if there exists a sequence S n of simple monotonically increasing functions, again in fact non-negative, we can also say they are non-negative, simple measurable non-negative sequence of functions which are monotonically increasing to the function f. That means, if a function f is non-negative and measurable, this can happen if and only if S can be written as a limit of simple functions which are non-negative and the sequence S n is increasing. So, let us prove this fact. So, let us start with, so let f is from x to r, and we are given a sequence such that there exists a sequence S n of simple non-negative functions S n increasing to f. That means what? That means f of x is limit of n going to infinity of S n of x for every x belonging to x, and these S n's are monotonically increasing. So, this is written as this. So, to show non-negative simple functions, and each is simple, of course, measurable, right. So, to show that f is measurable. Now, so let us let C belong to R, and let us look at the inverse image of the interval C to plus infinity. So, what is that? That is all x belonging to x, say that f of x is bigger than C. So, it will be easier if we look at the other set. So, let me, instead of this, let me look at the set which is f inverse of minus infinity to C. You will soon see why I am taking this instead of the earlier set, why I am taking this, because this proof becomes slightly simpler. So, what is this? This is all x belonging to x such that f of x is less than or equal to C. And what is f of x? Recall, so just now we said f of x is limit n going to infinity of S n of x, and S n x is increasing. So, if the limit of S n x, which is f of x, is less than or equal to C, that means each S n has to be less than or equal to C, because even if one goes above C, then the limit has to be bigger than C. So, this condition implies that S n x is less than or equal to C for every n bigger than or equal to 1. So, implies that the set f inverse minus infinity to C. So, if x is such that f of x is less than or equal to C, that implies S n of x is less than or equal to C. So, that means this is contained in, this is for every n. So, this is contained in intersection n equal to 1 to infinity of all x, such that S n of x is less than or equal to C. And if conversely, if, so note, if S n of x is less than or equal to C for every n, then this automatically implies that f of x, because f of x is the limit, that also is less than or equal to C. So, hence, so what we are saying is, in this is actually an equality. So, hence f inverse of minus infinity to C can be written as intersection n equal to 1 to infinity of x, such that S n of x is less than or equal to C, and that is same as n equal to 1 to infinity. So, this is S n inverse of the interval minus infinity to C, and S n's being simple measurable functions, each one of them is an element, each one of these sets is an element in the sigma algebra S. So, implies that f inverse of minus infinity to C belongs to the sigma algebra S. So, that means hence f is measurable. So, what we have shown is, if there exists a, so what we have shown is, if f can be written as a limit of an increasing sequence of simple measurable non-negative simple measurable functions, then f is measurable. Let us look at the converse part of it, which is going to be slightly not so obvious. So, conversely, let f from x to is a non-negative function. So, 0 to plus infinity be measurable. So, we want to show to construct a sequence S n of functions say that S n, each S n is simple, non-negative, S n is increasing to f. So, this is all we want to do. So, this is construction is intuitively very obvious, but needs to be explained. So, let us look at it in a picture. So, here let us draw a picture of the function. So, let us draw. So, this is x axis and this is the values, the real numbers, they are all values are non-negative. So, the graph is going to be above the x axis. So, this is going to be the graph of the function f of x, and the range of the function is a subset of 0 to infinity. So, what we are going to do is we are going to partition the range first into smaller intervals. So, to do that, let me draw a picture on a slightly bigger piece, so that we are able to look at. So, this is the graph of the function f of x, and this is x. So, let us mark off, let us put a point n here. So, this is the point 0. So, from 0 to n, and then from n to onwards. So, we are dividing the range of the function. The range is a subset of 0 to infinity. So, we have divided the range. So, I am writing 0 to plus infinity as equal to 0 to n open and union with the closed n to plus infinity. So, I have divided the range into two parts, and now next what we do is the portion 0 to n. So, this portion from 0 to n we am going to divide for every n into smaller pieces of length 2 to the power n. So, cut it into pieces, right, so that the length of each piece. So, length of each piece is nothing but 1 over 2 to the power n. So, this is the length of each piece. So, let us call the interval. So, this is my general interval. So, the upper point here will denote it by say k minus 1 by 2 to the power n, and the lower part as k by 2 to the power n. Okay. So, I am going to write this is equal to, so, and we are going to look at open at the bottom, closed at the bottom, open at the top. So, I am going to write as union of intervals of the type k minus 1 by 2 to the power n, comma k by 2 to the power n, union, that other part we leave it as it is n to plus infinity. Okay. And this union, how many such small pieces will be there? Total length from 0 to n, each has got sub interval has got length. So, 2 to the power n. So, this starts with k equal to 1 and goes up to n times 2 to the power n. So, this is what we do. Now, for every n I want a function S n of x. So, for any x, look at the value of f of x. So, let us look at those values. So, for every for x belonging to x, f of x belongs to 0 to infinity, right. So, that means, and so this union is a disjoint union. So, which let us write. So, f of x belongs to that partition that we have designed. So, k equal to 1 to n times 2 to the power n of the interval k minus 1 by 2 to the power n to k by 2 to the power n open, and this union n to plus infinity. So, now if f of x belongs to this and this is a disjoint union. So, f of x will belong to only one of them. So, implies either f of x belongs to n to plus infinity, or f of x will belong to one of these sub intervals. So, let us call it as k minus 1 to the power n over k by 2 to the power n, right. So, these are the two possibilities, and now we want to define a function S n. So, define S n of x we want to define. So, what should be the value of it? See, if the value is bigger than n, if f of x is bigger than n, then let us keep the value to be equal to n. If this happens, if f of x belongs to n to plus infinity. Okay. And let us define it. So, if f of x is inside this k minus 1 by 2 to the power n to k by 2 to the power n, let us take the lower value. So, let us so define S n x to be equal to 2 to the power n if f of x belongs to k minus 1 by 2 to the power n to k by 2 to the power n. So, this is how we are going to define the function S n. So, let us look at from the picture point of view. So, what I am going to do is, so because this is the range of the function, so f of x is going to be somewhere. So, if f of x is above n, above this line n, say for example, that is happening here this is the function, then for all these points my S n is going to be so it is going to be S n is going to be this constant. As soon as the function crosses n, the value of S n is going to be that part. And what is the other possibility? That f of x lies in one of these intervals. So, let us say f of x is here. So, this is my f of x. Then what do I want? My value of S n should be such that the difference between S n and f should be small, and this is the smallness we have created. So, I will define my S n to be the lower value. So, this is going to be my S n. So, as soon as the function is inside this strip, wherever the function is inside the strip, the value is this lower value. If it crosses n, then that is the constant value n. So, the function S n x is defined to be equal to this. So, this is S n of x is n if f of x is bigger than or equal to n, and if it is strictly less than n, then it will belong to one of those small pieces, and that is defined as the lower value of that interval as the value of the function S n of x. So, our claim is that this is the required sequence. So, claim this is the required sequence. So, let us first observe what is S n. S n is defined as this. So, I can write S n of x to be equal to n times on this interval. So, it is n times the indicator function of the interval n to plus infinity of x. If the point belongs here, this number will be 1. So, the value will be n plus, if it lies in that interval k minus 1 by 2 to the power n to k by 2 to the power n, the value is this. So, it is this value times the indicator function of that set. So, it is summation k equal to 1 to 2 to the power n times 2 to the power n of the indicator function of. So, what is that set? That is nothing but the f inverse image of k minus 1 by 2 to the power n and k by 2 to the power n open of x. So, from the picture, from the earlier formula, we get that my function is this function. Okay. So, it is clear from this, it is so implies S n is non-negative, simple, measurable. Why it is non-negative? Because n is the value taken are either n or the in multiplied this by k minus 1 by 2 to the power n, that value we forgot to multiply. So, either it takes the value k minus 1 by 2 to the power n or n, all are non-negative numbers. So, this is a non-negative function and it is a linear combination, finite linear combination of characteristic functions of this is not n to infinity. So, this is f inverse, right. So, let me just we should be careful. So, it is n if f of x belongs to this, that means, x belongs to f inverse of n to plus infinity, and f of x belongs to this interval means x belongs to f inverse of this interval. So, that proves that S n is a. Now, why are these sets measurable? It is a linear combinations of indicator functions of sets, and this set is measurable because f is measurable. This set is measurable because f is measurable. So, f is measurability of f implies that inverse images of intervals are elements in the sigma algebra. So, these are elements of the sigma algebra, and hence S n of x is a linear combination of indicator functions of sets in the sigma algebra S. So, it is a simple measurable function. And now, let us prove that this is S n is. So, claim we want to show S n is increasing.